we discussed in the earlier discussion. And then after that, we can have a short discussion of the entire day and then kind of wrap it up. So I think the thing that hasn't been discussed was Paul McFadden's talk. So Paul, can you tell us a bit about simplices?
Hi, everyone. Yeah, so we've heard a lot from the talk about sort of the bootstrap philosophy for constructing correlation functions into sitter, and there are two halves here. First off, we start with the symmetries. So for just scalar correlators, this would be the conformal ward identities, and then we apply boundary conditions for these, which are essentially looking at singularities. So Bunch-Davis vacuum at early times would correspond to no collinear singularities. And we could take the flat space limits where cosmological correlators reduce the scattering amplitudes, and then we could look at the factorization channels and so forth. So we've been looking at conformal field theory, and we have a result which fits in very naturally to this program. The starting point is, in many ways, the starting point will be, what are the solutions of the conformal ward identities? What's the general form of a scalar endpoint correlator in momentum space? And once you've got that general solution to the conformal ward identities, that's telling you the most general correlator that's consistent with de Sitter symmetry. Once you've got this general solution, then you can start imposing these extra sort of boundary conditions. Yeah, so our new result is that we found the general form of the endpoint correlator in momentum space, and you can think of it as a sort of Feynman integral with the topology of a simplex. So if you've got n points, you make a simplex by drawing a propagator between all of those n points, and you have a sort of generalized propagator for each line of the simplex.
Well, why don't you share your...
Yeah, okay, I can do that. Can everyone see my screen?
Yes, yes.
Yeah, that's right. So if you think in position space, of course, we know the form of 2- and 3-point correlators. And if we're talking about endpoint correlators, we know that they're functions of these conformal cross ratios. So for cosmology, we want to know what's the analog of this result in momentum space. What does a form of the arbitrary endpoint function look like in momentum space, and what there's got to be the same number of degrees of freedom in momentum space as there are in position space. So there's got to be some arbitrary function of some sort of variables that are analogous to the conformal cross ratios in position space. Yeah, so we've nobbled this problem, and so the solution is basically a Feynman integral over a simplex, and the general structure looks like this. So for every leg of the simplex, you've got a generalized propagator. You impose momentum conservation at every vertex of the simplex, and then you just integrate over the remaining momenta. And you've got an arbitrary function of these cross ratios, but the point is these cross ratios are constructed out of the momenta running between the legs of the simplex. So Qij is momentum running from vertex I to vertex j on the simplex, for example, like this. So yeah, so basically the general endpoint function in momentum space, it's a Feynman integral to the topology of a simplex, and you've got an arbitrary function of these cross ratios, which are constructed out of the internal momenta on the simplex. So I think it's sort of very interesting to think about this as a starting point for cosmological bootstrap program. This is the general solution of the conformal ward identities, and now we can start imposing extra conditions like absence of collinear singularities and the right behavior in the flat space limit and so forth. So sort of as a warm up in that sort of direction, we sort of looked at computing. So for example, if you have a contact Witten diagram, what's the form of this arbitrary function of conformal cross ratios that appears? And in some sense, if you're going elephant hunting, you want to know first off, what does an elephant look like? So as a first approach, we can just use some sort of brute force calculations to work out what this arbitrary function of these momentum space cross ratios is. And you can do these you can sort of do the calculations by thinking about analogies to electric circuit theory. Because we're writing a endpoint function as a Feynman integral over a simplex, you can Schwinger parameterize everything so it looks like a sort of Gaussian, and then the power dissipation that appears in the exponent. When you Schwinger parameterize a Feynman integral, the exponent is like the power dissipation in an electrical circuit. And of course, there's all these glorious old theorems that relate electrical circuits with different topologies. So for example, if you have a star-shaped electrical network, you can always rewrite it as a simplex-shaped electrical network. And so we can use these sort of electrical circuit analogies to construct the simplex representation of contact diagrams. So so that was sort of the discussion in the talk. So for example, at the level of the 3-point function, we know in momentum space the 3-point function is an integral of 3 Bessel functions. You can think about that holographically, of course, as 3 bulk boundary propagators. And using these tricks, you can rewrite it as a 1-loop triangle integral, which is the corresponding simplex when you've got 3 points. And so in my talk, I was just sort of explaining how to do that at higher points. So for example, you have a 4-point contact diagram. You can write it as an integral of a tetrahedron, which is the right simplex. And the arbitrary function that appears turns out to be a triple K integral of these momentum space conformal cross ratios. So I think it'd just be sort of interesting to sort of think about this as a starting point for the conformal for the cosmological bootstrap program. This is the general solution of the conformal word identities in momentum space, and now we can go and now we can supply further physical information and try and sort of construct cosmological correlates, very much as we've heard in all these bootstrap talks. Okay, probably a spot to start. Any questions?
Any questions?
I have a question, maybe. So I don't know how far you have gone in trying to find this simplex representation for exchange diagrams, but it looks like this simplex representation doesn't distinguish between different channels or things like that. So can you comment on that? Do you have any expectation of how this would look like? Or
yeah, I mean, that's right. So it's still sort of work in progress, but the methods I was talking about in the talk, the sort of electrical network analogies would work for exchange I mean, first off, of course, exchange diagrams, you can write them as a sum of contact diagrams. So in principle, everything's there. If you want to think about exchange diagrams, again, you can use these sort of electrical circuit analogies. You'd have an electrical network of resistors with an exchange topology, and then you could rewrite that as a simplex topology. So I think that's how you go about rewriting exchange diagrams in this simplex form. Yeah, so then what we could look at is summing over the different channels and seeing what. So for each channel, you'd get a particular f hat, and then when we sum over a particular function of conformal cross ratios in momentum space, and then once you sum over the channels, we can see what happens to this arbitrary function. So I think the idea is to get away from to get away from thinking about, of course, not every CFT has a holographic description. So this is a general result for all CFT correlators. Yeah, the different channels would just correspond to sort of permuting the operators in this correlator. So
I mean, this is already symmetric under permutations, right? So I don't think you need to sum over different channels to get something which is symmetric permutations. So.
Yes, that's right. So if you're starting from a Witten diagram, like an exchange diagram, you could compute what f hat was for this particular diagram. Then you could sum over channels to work out what the general f hat is. But if you're talking about a bootstrap philosophy, it would probably be more natural just to start from this general answer, which has permutation symmetry under swapping the operators around, and then you would try and impose. Yes, so the question will be sort of what are the additional principles to impose that then fix to particular cosmological diagrams.
Can I ask a question? How does crossing looks like in terms of these momentum space cross ratios?
Yeah, that's right. So it probably looks pretty similar to in CFT, doesn't it? So
it's exactly the same, U to V in the 4point.
Yeah, let's see. I think it does because.
No, but I mean, this is automatically cyclically symmetric, right? So it doesn't, you don't need to do anything with the U hats and the hats. The pieces are just sitting in the momentum conserving delta function.
Yeah, I mean, the representation is symmetric, of course, under swapping all the momentum around.
Yeah, but I guess like in position space, you can write crossing and f of u and v goes to f of v and u. And of course, the correlator is crossing symmetry, but you can write the action of crossing. What does it correspond to crossing in terms of the cross ratios?
I think it would be the same. So I mean, I mean, you can sort of see from here that the form of the cross ratios in momentum space look the same as in position space. So that's fine. If we swap P1,
I see. Okay, now I see it.
Question, does this form capture vile anomalous things where you violate the conformal word identities by local terms?
Yeah, so it's the same, it'll be the same story as it is for the 3-point function. So if we look at, for example, the 4-point function is given by this tetrahedral integral, and this is for this representation is for general operator dimensions, but as you take the operator or the space-time dimensions to special values, this tetrahedral integral develops singularities. And so, this is like, so to remove those singularities, you need to add counter terms, and then those counter terms, of course, are these local solutions of the conformal ward identities. So in terms of this solution, what happens is that as you go to these values where the Feynman integral develops singularities, you think about this in dimensional regularization, and the coefficient of that leading singularity in dimensional regularization is a local solution. So yes, this general answer captures all the local solutions. They're basically just the coefficients, the leading singularities.
So and the anomalies are always logs?
No, well,
the not fulfilling.
So for the 3-point function, they're logs. For the 3-point function, anomalies are ultra local. They're analytic in all the squared momentum. But you can have beta function contributions, which are like which behave like the 2-point functions. So they're non-analytic in just one squared momentum. When we're talking about higher point functions like endpoint functions, I would expect the anomaly. I would expect you can probably get sort of non-analytic.
Okay, yeah. So for the 3-point function, you're saying I get the log, and when I do a scaling, the amount by which I don't fulfill the word identity is local in the sense P1, P2, P2, P3. Okay.
You can have both semi-local and local ones. You can have log square pieces. So if you are in endpoint functions, I think you can have log to a power.
Yes, so the 3-point case we sort of analysed very thoroughly in this series of papers, and then for the higher point function, we're still sort of working out the details, but for the 4-point function, we worked out the cases where the singularities arise. So these are the cases where you would need to, where anomalies and beta function would arise. So we've classified those cases, and you can check from the form of this tetrahedron integral that you do get singularities in these cases that correspond to anomalies and beta functions. So it all behaves as we expect. We just need to sort of work out all the details.
Sorry, the claim is that if you look at a 4-point function, depending on the weights, you can have log squared appearing?
But for the 3-point function, actually, this is true. We had examples for 3-point functions where we got log squared. I can't remember, it's in our papers. I forget what correlator it was. I mean, Schwimmer looked at this recently as well.
I think for 4-point functions, probably they're going to be log cubed. So.
Yeah, a marginal operator in the equals 4 3-point function has log cubes.
I see. Interesting. Can I ask, did you guys try applying these weight shifting operators to your formula to see how the structure changes?
Yeah, that's right. So this is kind of also something on the menu to look at, but we sort of understand how this works. Back in the days when we were thinking about 3-point functions, we were showing you earlier the 3-point function you can write as a as a triangle integral, like this. And so you can construct weight raising operators for the 3-point function is straightforward to construct if you just differentiate this triangle representation of the 3-point function with respect to the external momentum. You raise the powers on these propagators, and that's like shifting the weights, the conformal weights of the 3-point function. You can also think, of course, the 3-point function has a representation as a triple K integral with 3 Bessel functions, and there are differential operators in external momenta that shift the weights in this Bessel function. Mm-hmm. So it's right. So for the 3-point function, we sort of already constructed the weight raising operators, back in the days, and I think the same approach should work for the simplex integral. It's a generalized Feynman integral with the topology of a simplex. You differentiate with respect to the momentum, that changes the powers of the propagators. So in some ways this would be an alternative derivation of your weight raising and spin raising operators. And of course, there's this sort of derivation from the embedding picture, but you could also just start from simplex representation, which is the general solution to conformal ward identities, and then you can see which are the operators that raise the powers of propagators, and that would be the analog of the sort of weight raising operators.
Right.
So I think in some ways, I think that this, you could start from the simplex integral and then use that as a template to work out what all these operators are. This will give you an independent derivation that's sort of quite easy to diagram.
They act pairwise though, so I wonder if that will mess with the symmetry of.
No, the pairwise structure is quite natural because these operations arise by integration by parts. So we for example, like for the triangle, you would differentiate by differentiate respect to external momentum P2, I shift the power of this propagator here, and then that would give you, in the numerator, it would give you a Q plus P, and to eliminate that Q, then integrate by parts a second time. So that generates the other differential operators. So yeah, so the bilocal structure of these spin raising and weight raising operators appears quite naturally just from integration by parts.
I see. Cool.
Can I ask a question? I guess you can do this procedure just for a single conformal block or for a single conformal partial wave, which are do you know what how to do it in some examples? I mean, there are examples in which conformal blocks are available in a closed form. Maybe there is. I would like to see what is this F hat.
Exactly. No, that's right. That's another sort of question on our agenda. So that's right. So what's a partial wave? So this is a general representation. What's a partial wave decomposition for this? So that's right. So one thing would be to look at examples where we know the conformal partial wave decomposition explicitly, for example, in position space, and try and work out the analog of that. Another approach would be just to, we can think of the conformal partial waves as being the eigenvalues.
You can solve directly for an equation for F hat.
Yeah, that's right. So we could start with the conformal Casimir equation, and we could hit the simplex with the conformal Casimir and look for the sort of eigenvectors. And so when you act with a conformal Casimir, you would end up with some differential operator acting on F hat, and so you'd have to solve this. You'd end up with a partial differential equation F hat, which you would have to solve, and that would tell you the conformal partial waves directly. So I think that's probably the way we would go about doing it. But yeah, so that's right. So there's a lot of sort of good open questions right now, isn't there? In some sense, making contact with explicit results of the bootstrap program we've seen so far, where we're talking about conformally coupled scalars, massless scalars, graviton exchanges, all the sort of de Sitter diagrammatics we've been talking about. And then there's also the fundamental questions related to CFT bootstrap program. What are the conformal partial waves? What's this arbitrary function of momentum space cross ratios that would tell us about the partial wave decomposition? And can we do CFT bootstrap in momentum space? So there's lots of great open questions right now. I mean, in some sense, it's a great time.
I wanted to add one other open question, maybe not a great one, but I was wondering how many of these results then come from unitary time evolution in the bulk. So this is related to what we discussed the other day. There is this relation, this cosmological optical theorem, which actually we have for all contact diagrams for any n, which is also something that here you have easier access to for all contacts. And so in particular, the constraint gets very interesting and non-trivial, especially when you have a logarithmic. So when you have these anomalies, these logarithmic terms, because that relates real and imaginary parts in a highly non-trivial way, which is why I was also asking if you get something more complicated than logarithmic, because basically the relation is very simple. It says that psi n plus psi n star evaluated at minus the energy has to be 0. So when you have things with complicated branch cuts, you're going to get very particular contributions from that need to cancel. So I was wondering, is it clear for you that there should be solutions of your equations that do not satisfy that? So that could be already a way to cut some of them out? Or
yeah, I mean, I suppose it's early days. I mean, in some sense, yes, that's another sort of thing we'd like to understand. Because we're writing correlators as generalized Feynman integrals, we can use all the sort of standard tools from Feynman integrals for understanding the analytic structure, the discontinuities, so yeah, to be sort of, I mean, because Polякov, of course, had this sort of famous work from the early 70s about sort of trying to understand, like in momentum space CFT, you take the discontinuities and it factorizes, and so we'd like to sort of understand some of that sort of analytic structure starting from this simplex representation. I think actually, I mean, the comments you were making though, I think it was also something we sort of understood. I feel like we sort of understood some of these results earlier, because when we think about things in terms of holographic cosmology, we had this very explicit mapping between CFT correlators calculated in ADS and cosmological correlators in de Sitter. And so some of these cases where you get logarithms, like for example, correlated 3 massless scalars in de Sitter, there's a logarithm that develops in that, and we understood that via these holographic formulae, because in the CFT for 3 marginal scalars, you get an anomaly. You have to normalize the CFT correlator. So again, you get a logarithm, and when you plug that into the holographic formula, you get back exactly the cosmological correlator on de Sitter. And the point you were making about the connection between the
the logarithm is definitely not something we have figured out, but well known. But the fact that by unitarity says that if you have a logarithm, you're obliged to have an imaginary part with precisely the same coefficient in the wave function. Otherwise, the theory does not come from unitary evolution.
Yes,
that's the concept.
Yeah, so we sort of found the same observation in the past via this holographic cosmology mapping, because when you renormalize it, the holographic cosmology map involves taking the imaginary part, and again you get the same relation between these coefficients that you were talking about. I mean, there it's coming about because the holographic mapping involves taking the imaginary part of a correlator, and for you it's coming about via the optical theorem where you're taking the imaginary part of a correlator. So it's not. I suspect there's a relation there, but I mean, I'd need to look at the details.
Oh yeah, I'd love it if you send me. Do you have a reference in mind? What paper?
I never wrote it up. I gave a talk in 2015 where I went through some examples of this, but yeah, I never wrote it up. But yeah, I can write it. I mean, I suppose our CFT correlators are from work in 2015, and then we have these earlier holographic formulae that we've sort of published, obviously, to get the cosmological correlators, and they involve continuing the momentum magnitudes and taking the imaginary part. And when you work out what happens for these cases where you get renormalization in CFT, you find these sort of behavior where the so I think there's sort of a connection to what you're saying, just because in your case, the optical theorem, you're taking the sort of imaginary part of diagrams, and in these holographic formulae, there's an analytic continuation of momentum, and then you take the imaginary part. So I think the same sort of phenomena arise.
I think in the CFT context, I think it is true that unitarity would impose conditions on F hat.
Yes, going back to that.
Because we haven't used unitarity, or this is the local general solution of the conformal worth identities. So any additional condition would impose additional conditions on F hat.
Yeah, so it's a great question, isn't it? So right, so time evolution in cosmology and de Sitter. What would those conditions impose on this function of momentum space cross ratios F hat? Yeah, so that's a sharp question, isn't it? And we could sort of study that, at least perturbatively, as a start.
But if I may add here, so this is Euclidean analysis. So in principle, we don't get any imaginary part, and indeed you have to analytically continue. But so this is first remark, and the other is, so these imaginary terms that you get, so these must be local terms, right? They must have locality, because there are some sort of commutators of some fundamental field or something like this. So they are always local. So in your case, in your presentation, right, this coefficient is just P1 cubed plus P2 cubed plus P3 cubed, which is just a sum of 2-point functions. And this, I believe this happens in general. So if you can classify, and you can classify all local terms, or in this case, this will be just all counter terms that produce such local terms, then you can figure out all these imaginary parts.
Yeah, so I suppose the general picture is just de Sitter space, which is essential. In the older holographic cosmology picture, bulk unitarity isn't the same as unitarity of this dual CFT, this putative dual CFT description. I think the point is that we've got a concrete framework to start addressing these questions. This simplex is the general solution consistent with conformal symmetry. Now we can start asking all these interesting questions about bulk unitarity. What does that impose on this function of cross ratios on the boundary? What's the boundary correlate of bulk unitarity? I mean, I think in some sense we've got a concrete representation for the solution of the word identities. Now let's go ask these questions. We've got a sharp framework where we can start addressing these questions.
But in particular, these Fs are going to have phases in them all over the place in the de Sitter. Right? When we have massive particles, we have oscillations. There's phases all over the place. So it's not, so it's not true these things are real, or they have to be the discount. I mean, they're. Actually, I had I had a question and a comment. So actually, just to make sure I understand, if I start with Witten diagrams, you can just say scalar Witten diagrams. You're just saying I do scalar Witten diagrams. I go to Schwinger parameterization for the propagators, and then it's just star delta on that Schwinger form that brings it to the simplex form. Is that right?
Yeah, that's right. Yeah. So just to run through it, exactly that. Yeah. So
okay, sorry, I just wanted to make sure I got the sort of summary right. So then I just had a small comment. Two comments. One of them is that I think this representation might make it might be the most convenient one to study the analog of the Landau singularities for the correlation functions. So that would be really cool to do that. That's at least one. I mean, that's one responsible way of figuring out where the singularities are as a function of the external data.
Yeah. So we sort of so like Arthur Lipstein and Joe Farrow, we were sort of look at this question. So like taking.
Right. I mean, and that should look very much because the sort of, well, I'm a little confused because of course you have denominators in the cross ratios as well, but most naively in your simplex form it's the same as what you'd get for an amplitude with exactly the same structure, of course, but there are the extra singularities associated with the cross ratios, which I guess I'd have to I have to think about more. The other little comment is that
Nima, they're not denominators with cross ratios.
Sorry, I thought, I mean, the cross ratios are like Q over QQ, right? So they're numerators and denominators.
Oh, you mean, sure. But they're not 1 over U's. I mean, the U's only appear.
No, I understand. But I just meant, if you wanted to think about where the singularities of this guy are, the singularities involving the Q's downstairs are the same as for amplitude, but there's maybe some more involving the actual cross.
Correct.
And the second little comment is that if your bulk theory happens to be planar, I mean, this is a little bit funny, but imagine we only care about planar diagrams, then your simplices will, your simplex is just a complete graph on endpoints, right? But you should reduce to just a planar graph, so it's even smaller. That's in n equals 4 land, people have I forget what they're called. They have some name, these graphs, but there's a fair, at 6 points you just have to look at, I think, a for loop diagram, like the sort of first diagram that you can make with the first diagram you can make with boxes. And it's just kind of cool that you can do. So if it's planar here, you just have the ordinary box at 4 points. And anyway, it's a much smaller problem. That's all I'm saying.
Actually, that's the point. Yes, that's the point I usually make in a longer version of the talk, actually. So like in many of these cosmological examples, the results just boil down to dialogues, which are fairly low order.
Exactly what we get from the box.
So what we expect to happen in this case here would be that these propagators that appear in the tetrahedron appear with either 0 power or dimension or power d, in which case they drop out.
Right.
So you'd either have edges of the simplex contract, or else you get propagators being deleted, and in both cases it reduces to lower loop order. So there are certainly cases where the tetrahedron, which is a 3-loop integral, reduces down to an acnode and then down to a box graph. So that's right. And I think this is what's happening in all these special cosmological examples that we've heard in these bootstrap talks, where we've got conformally coupled scalars, massless scalars, and we're getting answers that just involve dialogues basically, which are box integrals. So I think that's right.
Or things where there is an ordering. So when we have just a single signal too, that there is just an ordering. Yeah, I just want to say that, I mean, it's just a tiny comment, that people know ahead of time what the graph is. So if it's planar, it's just the graph, like at 4 points, just with one box. At 6 points, you put a box there, and then 3 boxes there, and then 5 boxes if you want to go to 8 points, and so on. So it's a tiny technical comment, but it's a lot smaller than the second you say the word planar, it's much smaller than the general.
And it's much more. That's right. So we got the dual momentum coordinates in that case. That's right. To make this connection to Grassmannians and stuff in that case. That's right. I mean, because the thing is, these CFT correlators in the flat space limit, they reduce at scattering amplitudes, and of course, we know there's all this sort of wonderful structure in scattering amplitudes. So Well, we'd expect some of that structure to persist into CFT correlator.
But the question about the Landau equations in complete generality, the simplex representation has got to be the way to set up the kind of that question. So that.
Yeah, that's right. Because we're just writing CFT correlators essentially in Feynman diagram language. So that's right. So we can bring in all our powerful tools from Feynman diagrams.
But can you elaborate of why is this representation convenient to do this Landau singularity analysis?
Just because we're writing things as a Feynman diagram, we're writing CFT correlators as a Feynman integral representation, so we can sort of use all our our usual sort of tricks for we know how to compute all the cuts in Feynman diagrams. We can use all that sort of tricks here.
But can you go back actually to from this form, can we actually formally Schwinger parameterize back to get, maybe before this final result? Can we see what what the Schwinger parameterized result looked like before?
For the Bessel K functions, or just in general?
In general, like if I start with some general, even with a general scalar Witten diagram, can we go through can you just repeat the sort of steps that you get to your representation? Yeah,
that's right. So of course, the simplex representation is a representation for any CFT correlator in terms of a general, but for a specific correlator like a contact diagram, there's a specific form of this arbitrary function. Yeah, so to find it, we start off just by Schwinger parameterizing the Bessel functions using this sort of standard.
Right. I see. Okay, got it.
And then we can do the radial integral inside the contact.
Right. So we can just leave it already at this point. After we do the radial integral, we can do the radial integral. We can do star delta to simplify it. Right. Yeah.
So the exponent in this Schwinger parameterization is literally the power dissipation in a star-shaped electrical network. So then we use to rewrite it as a simplex electrical network, and basically the Jacobian from the change of variables gets removed by adding currents that run around inside the simplex, and so that's basically just those are the two steps in the calculation. You just use star delta to change the topology of the electrical network. You've got Kirchhoff's laws relating the sort of resistors.
But normally when one does the Landau analysis, it's really most convenient from the Schwinger form, right? So you sort of start from the Schwinger form, and now so what does your Schwinger form look like? Even let's say we have a simple Witten diagram. So your Schwinger form just looks like.
So for the contact Witten diagram, this is the Schwinger form for the contact diagram.
Right.
So it's basically just an integral over a bunch of Schwinger parameters, which are these capital Zs, and they're like the resistors on the contact electrical diagram. And then you've got an exponential of basically the factor inside the exponential is just the power dissipation in this electrical network. So the momentum is like the current running in this network, and the big Z, the Schwinger parameters, they're the conductivities in this electrical network. Power is current squared divided by conductivity. So the idea is you want to rewrite your contact diagram with the contact topology as a equivalent Schwinger parameterized diagram with a simplex topology. So we just, the point about these two electrical networks is they got the same power dissipation, and the power dissipation is just this exponent here. So I can just rewrite this in terms of the power dissipation in the simplex, and the currents on the simplex are related to the currents on the star, and the resistors on the simplex are related to the resistors on the star, just by the sort of Kirchhoff rules for electrical circuits. So from a Feynman diagram point of view, this is giving us some rather non-trivial change of variables. So there's a change of Schwinger parameters, which corresponds to changing the resistors, and the Jacobians that come from this change of resistors are removed by adding currents, which are momentum loop integrals running around the faces of the simplex.
But we can't, so when you get to your final representation, I don't see the Schwinger forms anymore.
Oh yes, sorry, yes, that's right.
So you got rid of the Schwinger forms, right? You just used the Schwinger parameters to argue for the star delta movology. But then you go to a specific form. Why not reverse? Can you integrate it? Can you reverse the integrals and just and write it as an integral over Schwinger parameters directly?
So yeah, in some cases you can do all the Schwinger parameter integrals. So we've gone from the start of the delta form,
Right.
And we do as many of the Schwinger parameter integrals as we can to get rid of them. So for the 3-point function, we can completely get rid of all the Schwinger integrations, and we're left with just this one loop triangle integral, where the momentum loop integral around the triangle was
but
what we
I'm sort of asking the opposite. I mean, what one usually does in setting up, I mean, in the cleanest way of thinking about the Landau analysis for amplitudes, you actually keep the Schwinger parameters. You want to integrate everything else out and keep and only deal with the Schwinger parameters. Is the analog of that possible to do here or not?
I think
the previous slide, right? Can you move to the previous slide? This one.
Yeah. This is, of course, so this is the result for the endpoint contact diagram. So this is the arbitrary function of momentum space cross ratios, the f hat that appears for the general endpoint contact diagram. And in this case, you can't integrate out all the Schwinger parameters. Instead, you've just left with n-2 Schwinger parameters. So this result looks ugly, but it's probably familiar to you because it's actually just the endpoint polygon integral. If you do an endpoint, a one loop endpoint polygon integral, n-1 point polygon integral, and you Schwinger parameterize it, this is the form here. You've just got this. This is just like you've got your quadric in the denominator here, and then you've just got Schwinger parameters in the numerators. And so the only difference to the polygon Feynman diagram is that dot products and momenta are being replaced by these conformal momentum space crossovers.
Right. So great. So this is the closest analog to the integral with the quadric to the appropriate power downstairs. Right.
It's very, very close to the stuff you were doing with Alice.
Okay. Yeah, and let's see. So let's see. So we have I see. So it is quadratic in the Schwinger.
That's right. So it's basically so it's just like so for the 3-point function.
Right.
For the 3-point contact diagram, it became a triangle integral. For the endpoint contact diagram, we got.
I guess I'm just asking. I'm asking a more basic question. Is there an analog of the semantic polynomials for ABS? I mean, yeah. So and what the usual thing what we do when we Schwinger parameterize is we do all the loop integrals, so we're left with some giant integral over the Schwinger parameters. Yeah, does that analog exist in ABS?
Yeah, so that's what we have here on the slide. That's right. So the arbitrary.
For this example, but is it general? Do you know how to do it for a random graph? If I
the star delta thing's a general result, isn't it? You can always integrate out internal vertices on the graph. And
the equivalence, no problem. I'm just asking about whether it's possible to do the like ABS and the loop integrals and just be left with an integral of the Schwinger parameters.
I think in principle you should be able to do it. I mean, certainly we can do it for these examples here, and we're left with just a Schwinger parameterized integral here with the cross ratios. So I think
that would be very cool to know what the analog. I mean, for amplitudes, you give me a random graph, and we can integrate over all the loop momenta, and we're left with an integral over the Schwinger parameters with the semantic polynomials upstairs and downstairs. It would be awesome to have the Schwinger. If it exists, it would be awesome to know what the analog of the semantic polynomial. I mean, physically, this is the world line representation, right? That it's not just some random. It's the world line representation for the amplitude, and it has a lot of meaning. Not just the Landau equations, lots of other important meaning for how you see the UV divergences, IR divergences, all kinds of cool things come out of this thing.
You also need this representation for a bulk-to-bulk propagator, right?
Yes.
Because
so that's sort of.
You have it as well,
right?
Yeah. So it's that sort of next on our hit list, but the same tricks will sort of work because the sort of star delta type tricks. You can do it for exchange topology and rewrite that as a simplex topology. So yeah, so we haven't got the calculation finished yet, but I mean the same tricks will work. And that's right. So this is the Feynman parameterized version of the arbitrary function that appears for the contact diagram, and the semantic polynomial is just this quadratic one in the denominator here. We recognize this as the n-1 point polygon integral. And then the next step would be to look at the exchange diagram. What are the semantic polynomials that appear?
Although it's funny in this case, the graph, the Witten diagram is just the contact term. So it's sort of funny to get. That's. So whatever it is not going to be directly related to the usual semantic polynomials, because those involve cutting the graph and finding trees and so on. Here you're just getting it from a contact diagram.
Yeah, I think what's going on is that the endpoint Witten contact diagram is equivalent to a conformal star integral on the boundary, and then you go to the dual momentum coordinates, it becomes a polygon. So that's the connection. I think that's really that's sort of where the polygon topology is coming from. But yes, it's right. It'd be good to sort of understand this. I think once we've got a bunch of examples, then we can sort of think about this more generally. You know, how does your Witten diagram topology correspond to the the semantic polynomials, the electrical circuit topology that's appearing in this function of cross ratios. Yes, and then once you've got this sort of general Feynman representation.
I think for the purpose of understanding the singularities, just doing it with scalar Witten diagrams is perfectly good enough, right? You know, so whatever we get from that has all the singularities of the most general situation. Yeah, so yeah, cool.
I think we're already very late. We're 23, 25 minutes past time. So is there any last minute urgent question about either Paul or anything else? Okay, it doesn't seem like I have anything else. So thank you all for staying that late. And I guess I'll see you tomorrow at 1 UK time.
Right, see you all tomorrow.